12 billion liters of water punched through the concrete wall. With the force of a detonating nuclear warhead. The 12,000-ton block of the St. Francis Dam doesn't just crack. It liquefies at the base. And shatters into monoliths the size of apartment buildings. A 50-meter wall of black, churning liquid hammers into the canyon floor. Vibrating the bedrock so violently it registers on seismographs in Pasadena. Steel-reinforced concrete is ground into pebbles in seconds. Heavy machinery, massive steam shovels, and entire construction camps are pulverized. Their components twisted into unrecognizable knots of iron. The roar is not a sound but a physical weight. A bass frequency that shatters glass kilometers away. Before the water even arrives. Most turn away. But here at Surphysia, we decode the math behind the chaos. Support the mission by subscribing now. The catastrophe of the St. Francis Dam is not merely a story of bad luck. It is a clinical study in human ego overriding the fundamental laws of geology. To understand how a structure weighing millions of kilograms can simply vanish in the middle of the night, we have to look at the microscopic level of the soil. And the hubris of its creator, William Mulholland. This was a man who had built Los Angeles out of a desert. A man who believed that if he poured enough concrete, nature would simply have to obey. But gravity and hydrostatic pressure do not negotiate. They wait for a single point of failure. Let's slow down the clock. Before the first drop of water escaped on that night in March 1928. The disaster was already written into the very stone of San Francisco Canyon. The eastern wall of the canyon was composed of Pelona schist. Imagine a deck of playing cards tilted at a 45-degree angle. As long as the cards are dry, they stay put. But once you pour water between those layers, the friction disappears. The water acts as a high-pressure lubricant. The dam wasn't just sitting on a mountain. It was sitting on a giant, geological slip-and-slide. On the western side, the situation was even worse. The rock there was Sespe conglomerate. Red sandstone held together by nothing more than dried mud and clay. In a laboratory, if you take a piece of this rock and drop it into a glass of water, it doesn't just get wet. It dissolves. It turns into a handful of loose sand and pebbles in minutes. Mulholland, a self-taught engineer who skipped the peer review process, looked at this red rock while it was dry, and assumed it was as solid as granite. It was a billion-liter mistake. As the reservoir filled to its maximum capacity of nearly 47 million cubic meters, the pressure at the base of the dam reached staggering levels. Imagine the weight of the entire Eiffel Tower concentrated onto the palm of your hand. That is the kind of force the water was exerting against the upstream face of the wall. This pressure, known as hydrostatic head, doesn't just push forward. It pushes down, up, and into every microscopic pore of the rock. The water began to infiltrate the deck of cards on the east, and the sugar cube sandstone on the west. 5 days before the collapse, the reservoir reached its peak level. Just 10 centimeters below the spillway. The dam was screaming, but its cries were silent. Small leaks began to appear. Leaks that Mulholland himself inspected and dismissed as normal. He saw muddy water pouring from the western abutment, and concluded it was just construction runoff. He was wrong. That mud was the very foundation of the dam being washed away, grain by grain. The Sespe conglomerate was liquefying. Beneath the concrete, the uplift pressure was rising. In fluid dynamics, uplift is the silent killer of gravity dams. If water gets under the base, it exerts an upward force that effectively tries to float the dam like a boat. When the upward force of the water exceeds a certain percentage of the dam's weight, the friction holding the dam to the earth drops to zero. At 11:57 p.m., the eastern wing of the dam, the part resting on the slippery schist, finally gave up. The sliding plane lubricated by the rising reservoir finally lost its grip. Thousands of tons of rock slid downward, instantly removing the support for the concrete. The dam didn't just break. It tipped. When the eastern side failed, it created a massive internal torque within the main concrete body. The center section, a monolith nearly 60 meters high, was suddenly unsupported on one side. The physics of leverage took over. The water behind the dam, now a churning mass with a density of 1,000 kilograms per cubic meter, sensed the opening. It shoved. The initial breach wasn't a trickle. It was a blowout. A surge of water exploded through the eastern gap. And within seconds, the rushing torrent began to scour the base of the center section. Imagine a power washer. But instead of cleaning your driveway, the nozzle is 10 meters wide. And the pressure is high enough to strip the bark off a tree 5 kilometers away. This water carved a canyon into the soft Sespe conglomerate on the west side in seconds. The western wing collapsed next, falling into the void. All that remained was the towering center section, standing like a tombstone in the middle of a man-made hurricane. As the wall of water traveled down the canyon, it wasn't just liquid anymore. It was a debris flow. Because water is so dense. And its velocity was reaching nearly 30 kilometers per hour. It had the kinetic energy to pick up objects that should have been immovable. It picked up blocks of concrete weighing 10,000 kilograms. And tumbled them like dice. It stripped the soil down to the bedrock. When the flood hit the Southern California Edison Powerhouse No. 2, located about 2.5 kilometers downstream, the building was erased. Not knocked over. Erased. The workers inside never had a chance to hear the roar. The air pressure pushed ahead of the water was so intense. It likely blew the windows out before the liquid impact finished the job. The wave was now 40 meters high. To visualize that, stand at the base of a 12-story building and look up at the roof. That was the height of the water moving through the narrow canyon walls. As the canyon widened, the wave spread out. But it didn't lose its lethality. It just traded height for width. It hit the town of Castaic Junction, then surged into the Santa Clara River Valley. By now, the water was a thick, brown slurry of mud, trees, houses, and the wreckage of 1,000 lives. It carried the smell of wet earth and shattered pine, mixed with the sharp, metallic tang of pulverized machinery. The physics of a flood like this is governed by the Manning formula, which relates the velocity of the flow to the slope of the land and the roughness of the surface. But formulas fail to capture the sensory nightmare of the event. The water was moving so fast that it created a bow wave of compressed air and debris. Survivors described a sound like 1,000 freight trains passing through their bedrooms. The irony was that the very infrastructure meant to bring life to the desert, the pipes, the roads, the bridges, became the weapons of its destruction. Telephone poles became battering rams. Bridge girders became giant saws that sliced through everything in their path. By the time the surge reached the town of Santa Paula, 65 kilometers from the dam site, it was still nearly 8 meters high. It arrived in the dead of night. A silent assassin because the sound of the water was often muffled by the terrain. Until it was too late. People woke up to their houses tilting and the sound of wood splintering. The flood didn't just move through the town. It rearranged the geography. It deposited 2 meters of silt over entire citrus groves, burying the livelihood of thousands under a layer of suffocating mud. Why did the center section of the dam stay standing? For years, it was a mystery. But the math reveals the answer. The center section was the thickest and heaviest part of the gravity dam. It was seated just deep enough into the canyon floor that even when the sides vanished, its sheer mass kept it pinned by gravity. For a moment, it stood there, a jagged finger of concrete pointing at the sky, surrounded by a void where billions of liters of water had just passed. It was later nicknamed the Tombstone. It was eventually dynamited because it became a macabre tourist attraction. A monument to a failure so total that it ended the career of the most powerful man in California. When we analyze the St. Francis Dam failure through the lens of modern geotechnics, the mistake is blindingly obvious. Mulholland failed to account for pore pressure in the foundation. He treated the ground as a static, dry platform, rather than a dynamic, hydraulic system. He didn't realize that when you put a massive weight on top of soil, and then saturate that soil with water, you change the very physics of how that soil behaves. It's the difference between walking on wet sand at the beach and trying to walk on quicksand. One supports you. The other swallows you. The total energy released during the collapse was equivalent to thousands of tons of TNT. But unlike a bomb, which dissipates its energy in a sphere, the dam break channeled all that energy into a narrow corridor, maximizing the destruction per square meter. The velocity of the water at the breach reached nearly 15 meters per second. At that speed, water is no longer a life-giving liquid. It is a structural solvent. It dissolves the bond between bricks. It shears bolts, and it turns the very earth into a fluid. The aftermath was a graveyard of engineering hubris. Over 400 people were gone. Their bodies swept all the way to the Pacific Ocean, nearly 85 kilometers away. William Mulholland, at the official inquiry, famously said, "I envy the dead." His mistake wasn't a lack of effort. It was a lack of humility in the face of the Earth's complexity. He relied on visual inspections and gut feelings, where he should have relied on core samples and hydraulic testing. He ignored the fact that the red sandstone on the west side crumbled when wet, because he couldn't imagine a world where his concrete wouldn't hold. Today, the site of the St. Francis Dam is a quiet, scarred canyon. You can still see chunks of concrete, some the size of cars, scattered kilometers downstream, half buried in the wash. They serve as a reminder of the factor of safety. In engineering, we usually build things to be 3 or 4 times stronger than they need to be. Mulholland's dam had a factor of safety that approached 1.0 on the night it failed. In the world of physics, 1.0 is the edge of the knife. 1 millimeter of movement, 1 extra Pascal of pressure. And the transition from order to chaos becomes inevitable. We often think of our modern world as permanent. But the St. Francis Dam shows us how quickly our greatest achievements can be reduced to rubble. When we ignore the microscopic details, the interaction between water and rock is a slow war of attrition. That the water always eventually wins if the engineering is flawed. The schist slid, the conglomerate dissolved. And the gravity dam, meant to stand for centuries, lasted exactly 2 years. It was a failure of imagination as much as a failure of math. Mulholland couldn't imagine the rock beneath his feet changing its fundamental properties. He saw a mountain. The water saw a sponge. The tragedy forced a total rewrite of dam safety laws in the United States. It gave birth to the field of engineering geology. The mandatory recognition that you cannot build a structure without understanding the chemistry and physics of the ground it sits upon. We learned that the static earth is anything but. It breathes, it shifts, and when pressurized, it betrays. Every dam built since 1928 carries the DNA of this disaster. The deep grout curtains, the drainage galleries to relieve uplift pressure, and the rigorous testing of every pebble in the foundation. We pay for our progress in the currency of catastrophe. And the St. Francis Dam was one of the steepest prices ever paid. As the sun rose the next morning, the reservoir was empty. What had been a massive lake was now a mud flat. And the canyon downstream was a raw, red wound in the earth. The water had returned to the sea, leaving behind a trail of debris that stretched across 3 counties. The silence that followed was more haunting than the roar of the collapse. It was the silence of a lesson learned too late. A reminder that the laws of physics do not have a sense of mercy. They are consistent, they are brutal, and they are always in effect. When we look back at the jagged remains of the St. Francis Dam, we don't just see broken concrete. We see the limit of human certainty. We see the point where the blueprints meet the reality of a world that is far more complex than a slide rule can calculate. We see the necessity of doubt in the heart of every creator. Because the moment we believe we have fully conquered a force of nature is the exact moment that force begins to find the crack we missed. The universe is full of chaos, but we are here to decode it. Stay connected to Surphysia.